Hello, welcome back. So we're going to talk about some advanced techniques for machine learning. So in this section, we're going to talk about some special feature in engineering, regulation, how can we standardize some of this data, and how can we handle data leakage and validation. So feature engineering, we talked about slightly about feature engineering before, but so we're gonna go a little bit more in depth today on how we can modify some of the features. Remember, features is part of the data that input data that we provide to train our machine. For example, let's say that we are looking to predict what will be the price of a house in the future, and some of the information that we need to take would be probably the value of the house, how many months has been in in sale, posted to be sale, the size of the rooms, the location, sort of like that. Those information that is called a feature, and so every input value that we pass into the machine will have a value for all those different features. And so what this is doing is we're going to modify some of those features, what we call feature engineering. Feature engineering is the process of using domain knowledge to transform raw data into meaningful features that can be used to improve the performance of the machine learning models. So what are some of the examples? Transforming existing features. So we will take some of the features that we already have and we're going to modify them, creating new features from existing ones. So we could take one feature, one column, and generate other features, uh, and reducing the number of features. So we could exclude some of those columns, some of those features, because maybe not they don't make any difference to the actual uh, data prediction. So here's an example of a feature engineering encoding. Many models only work with numbers, so not text. So we convert categorical variables into numerical ones. This is called encoding. So for example, let's say we have a column, a feature called eye color. Now, a lot of the machine learning models cannot handle a text. So they don't know what to do with a text. So what we can do is we can assign a number to this to each of these uh, values of this column. So in this case, we have black, brown, hazel, blue, and green. So we can assign 0 to black, 1 to brown, 2 to hazel, 3 to blue, and 4 to green. So that's what we call encoding. So we just modify a previous feature. So this is transforming a feature from one to another, from a text to a number. And that's called encoding. Another one, here's more examples where we do feature engineering. Many machine learning algorithms can only understand numbers, not strings or other not numerical data. This means that we need to transform categorical variables into numeric values before feeding them into algorithms. This process is called feature engineering. So for example, let's say that we have a feature that has the names of a state, for example, Arkansas, Texas, Montana, New Hampshire, right? So we want to be able to assign a value, a number to every single state, right? Or we can have the highest degree someone has, so for example, GED, high school, bachelor's degree, master's, and PhD. Or we have the seasons of the year: spring, summer, fall, winter. So for example, we could have a feature that in to predict the the sales of a house, and we can see that one of those columns, one of those features is the season. So maybe during the summer people buy more houses, or and during the winter they don't, or whatever, something like that. But so we imagine that we have this column, and we can't just have spring, summer, fall, winter, because we won't be able to train our model. So we can change that to be represented by an integer: 0, 1, 2, 3, or 4. Here are some examples of another more in depth about feature engineering. There are several ways to encode categorical variables. The way you encode this feature changes how effective you could changes how effectively your model algorithm is. So here's 4 ways to do encoding. So remember, encoding is to change a text to a number, and one of them is called label encoding. So for example, label encoding is used to encode nominal data categories with no natural order. So this is referred to when a set of data that's like, for example, strings that we want to turn into numbers does not have a particular order. There's no order relation. So here we can just randomly select them. Like for example, apples, oranges, and bananas. There's no order of value between assigning between the apples, oranges, and bananas. There's bananas are not higher than oranges are not higher than bananas, and so on. So there's no specific order that we can assign here, right? So the order doesn't really matter. Hair colors: brown, black, blonde, red. So that really doesn't really matter the order, right? There's no order value. Nationalities, and in this list that we're actually talking about, each category is assigned a value, typically starting at 0. So we can randomly select assign a value between 0 and however numbers we have. So that's what we call label encoding. There's no specific order that we need to follow. The other one is called ordinary encoding. Ordinary encoding refers to when the actual data list does have a value in hierarchy. So let me give you the definition, right? Ordinary encoding is used to encode ordinary data with natural order when there's actually a specific order in which you want to be able to follow, or sequence. Note that the outcome can only look the same for label and ordinary encoding, but the logic is different. So for example, income levels, that could be in order, right? Education levels: high school degree, bachelor, associate, bachelor's, master's, PhD, right? So that does have an order, so we can assign an order to those to the list. Satisfaction rating, we can assign a order, and the way we actually use that is we in Python we import this from the sklearn preprocessing. We import this ordinary encoder, and we create this object, an ordinary encoder, that so we create an object here, and we use this object to be able to call a method fit transform to encode our data. And this is gonna be now our data in being assigned an ordinary number. So it has been changed from strings to a numerical order. And then there's the other one, which is one-hot encoding. One-hot encoding works for categorical variables where no ordinary relationship exists. One-hot encoding creates a new binary for each category. For example, you have a variable called animal that has 5 categories: dog, cat, sheep, lion, and horses. That assigns a binary number assignation for each column. So what it does, it turns one feature into this case five different features. So this is what we call the example we were talking about, creating new features from existing ones. So we took one feature that had a label for the animals, and we turned it into we added into 5 new features. Okay, so what we do is we assign a value 1 for the cat, for the dog. If you have a dog, 1 for the cat, 0, 1 for the cat, 0, 0, 1 for the sheep, 0, 0, 0, 1 for the lion, and 0, 0, 1 for the horse. So in this way, the advantage of doing this is that we're not assigning a value in which the order. So remember when we did the ordinary encoder, if we assign a 1, 0, 1, 2, 3, 4 to our list, we're kind of giving them a priority, right? There's a priority that, maybe 4 has a higher priority, so that PhD will be higher value. When we did that same thing with the label encoding, unfortunately, even if we didn't try, we are given some value to the to each of the different values of the feature, because we're assigning a number. Now numbers will be, unfortunately, take in consideration when you train the machine. So unfortunately, we are assigning a value, some value that we didn't want, some relationship that we didn't want to add. So we have to be careful when we encode our features because that could and unintentionally we can add um, some weight to some of the to some of those different classifications values. So now the one hot encoding prevents that because in here we're not assigning any. There's no value like 0, 1, 2, 3, 4, right? So the 4 doesn't exist. They all have the same value of 1. So this is what the hot encoding uh, has a benefit, but unfortunately, it does create a lot of features, which makes your machine learning heavy, right? It will take a lot more longer to process. Dummy variable encoding is practically the same thing as in hot encoding, but with one less feature. So it is a little bit quicker because it has one less feature, but it's practically almost the same. And if you actually use it, you use a you use the you from the ASCII preprocessing you import the one hot encoder and you use the one hot encoder drop the first to create this object and we use this object to transform our data. We practically do the same thing for the one hot one. We practically do the same thing. We import the one hot encoder. We create an object and we use it to fit our data. So that's gonna create all the other features. Here's practically what I was a summary of what I was talking about. Pros and cons of using the label and ordinary encoding. The label and ordinary encoding pros will be simple to implement, can handle non-numerical category variables, so that's good. The cons is that it can lead to overfitting, can introduce an arbitrary ordering to the categories, so that's what I was talking about. Assumes ordinary relationship between categories, not always true. So it could create this relationship that we didn't have. Note since outcomes look similar for label and ordinary encoding, most of the pros and cons are the same. One hot encoding, most popular, can improve model performance, can handle non-numerical category variables without assumption about ordinary relationships between categories. So that prevents the relationship that I was talking about. And so, but the downside is that it can increase the dimensions of the data set, which can slow down the training and evaluation to the model. So this is going to add more features to the database and to the data, which in the end, when you try to train it, it's going to make it heavier. It's going to make it a little slower. It can lead to sparse data, multi-collinearity, and require more computational power. Dummy variable is very similar to the one hot one encoding. It can handle non-numerical category variables. It is similar to the one hot encoding. It can increase the dimensionality of the data set, which can slow down the training and evaluation model, which is the same thing as the one hot one. It can lead to sparse data and require more memory to store, of course, because we have more features. It can lead to multicollinearly if some categories are highly correlated. When you use each, when to use each labels in order to record it, you want to use them when there is a large number of categories or category variables has a clear ordinary recording. So when we do have a specific order that we want to follow on our data, so we want to be able to transform that feature data values into a number. So when they do have an order that will be perfect if we're going to use an order encoding. One hot encoding when used when the categories of the category variables are independent of each other. When the values of your features, right, you have let's say you have a feature column, the values of that column are independent of each other, then we want to be able to use it one hot encoding. For example, sedan hashtag. So let's say you have a car, and the values of your car feature is sedan, hatchback, SUV, coupe, convertible. They're independent of each other. So that will be a perfect time to be able to create a hot encoding. Dummy variables we use when you want to introduce, when you include a category variable in a linear regression. This is practically the same thing as the one having coding one. They're practically almost the same, but with just one less uh, feature. So now another thing that we want to be able to talk about when we talk about feature engineering is called scaling. So for the model to work effectively with numerical data, the features need to be numerically comparable. This requires scaling the numerical features. So what does that mean? There's two different ways of scaling your data. One is called standardization and the other one is normalization. So the advantage of using this is that, for example, let's say you have a feature and one of the feature in that feature, the values of your data are between ranges between 0 and a million. So in that sense, if you compare that values of that feature compared to another feature that has values between 1 and 10, of course, the features that ranges between 1 and a million is going to have a heavy influence on your training and predictions. And we don't want to do that. We want to have all the features to be relatively equally represented in the data. So that is when we could normalize and standardize our data. Usually you want to go first with normalization and then standardization. So we'll talk about specifically about each one, normalization and standardization. But here's the formulas that that defines this standardization and normalization. I'm gonna change to the next video.